Chemical change in iron. Corrosion is caused by the transfer of electrons. Chemical change in batteries. Electron transfer can produce electric current. Chemical change in water. Hydrogen and oxygen are formed when water is split by the transfer of electrons. 3 examples of chemical reactions. All involve the loss and gain of electrons, and all are part of the huge class of chemical reactions called oxidation and reduction. Oxidation and reduction. One of their effects is corrosion. It's a common but complex series of chemical reactions. Metal atoms give up their electrons to other elements, often oxygen. The metal atoms are said to oxidize. Iron and steel form iron oxide, rust. Rust stimulates the production of more rust until all atoms are reacted. The runaway oxidation of iron and steel is a serious problem. Billions of dollars are spent each year to stop it. An obvious way is to keep oxygen and moisture away from the metal. That's one reason for paint. But paint isn't needed on all metals. The product formed when some metals oxidize actually stops further corrosion. The copper in bronze oxidizes to a green protective layer. It blocks out oxygen and moisture, protecting the underlying metal. Aluminum corrodes to aluminum oxide, a tough protective layer. Some environments can accelerate corrosion. It occurs much faster in salt water than in fresh. The reason is that salt water is a good medium for transferring electrons. So in salt water, the rate of oxidation is enormously increased. The oxidation rate can be increased even more by raising the temperature and by using a more reactive metal, such as magnesium. Don Showalter.
That was some chemical reaction, wasn't it? I heated a piece of magnesium ribbon. Now, that was quite a display of chemistry, but what does it have to do with electron transfer? Well, if you think about it, the magnesium lost electrons, and the oxygen from the air gained electrons, and it formed magnesium oxide. There's the connection.
Here's another example of oxidation and reduction. A strip of zinc metal is placed in a copper sulfate solution. A reddish deposit of copper metal forms on the zinc. Where does it come from? Each neutral zinc atom loses 2 electrons. It's oxidized. The copper ions in solution gain 2 electrons. They're reduced to neutral copper atoms. Can we harness this oxidation-reduction reaction to do something useful? Yes, in electrochemical cells. Not exactly a household phrase, but they're in every home as batteries. Batteries can raise the garage door, and they can raise the roof. Without batteries at hand, you'd be forced to leave your seat. Without batteries in your smoke detector, you could be forced to leave your home. In the heart pacemaker, they can prolong life itself. How do electrochemical cells work? How can we convert the oxidation-reduction reaction we saw earlier with copper and zinc into an electrochemical cell?
I've set one up here for you. This now is a copper-zinc electrochemical cell. It consists now of a copper electrode into a copper salt solution, in this case copper sulfate, and then a zinc electrode in a zinc salt solution. Again, it's zinc sulfate in this case. Now, I've connected it with this porous paper bridge. Sometimes you will see people use a porous barrier that's used in the same container rather than have 2 separate containers. And that will separate the solutions and allow the ions to come through there. We also have an external circuit here of wiring now that will hopefully carry the product of this reaction. This now is a chemical reaction that's going to occur, and it's going to produce an electric current for us. Let's see if it does that. I'll connect it here so we finally have a completed circuit, and watch the meter. There's the electric current.
But beyond these observations, how does this oxidation-reduction reaction produce electric current? A good place to start is at the zinc electrode placed in the zinc sulfate solution. Here on the electrode surface, here in the atomic world, there are numerous zinc atoms. And as each one moves into solution, 2 electrons are left behind. This is oxidation. On the electrode, electrons not only accumulate, they move. A constant movement of electrons. They push up into the wire, through the voltmeter, and onto the copper electrode in the copper sulfate solution. Here, positive copper ions are reduced. They combine with electrons from the zinc to form copper atoms. Positive zinc ions move within the solution toward the copper electrode. And negative sulfate ions move toward the zinc electrode. This balance of ions moving through the boundary keeps current flowing in the electrochemical cell. Why should electrons always move externally from zinc to copper? Different metals have different tendencies to give up electrons. Zinc gives up electrons far more readily than does copper. Commercial batteries use a variety of electrodes. In all batteries, they consist of 2 materials with different tendencies to give up electrons. When the electrodes are connected through an external circuit, electrons flow from one to the other. In the development of new batteries, there's been room for the backyard inventor. A better electrode was the invention of Wilson Greatbatch.
I quit all my jobs, and with the $2,000, I went out in the barn and back of my house, and I built 50 pacemakers in 2 years. I started making the rounds of all of the doctors in Buffalo who were working in this field, and I got a consistently negative result. The answer I got was, well, these people all die in a year. You can't do much for them. Why don't you work on my project, you know? When I first approached Dr. Shardak with the idea of the pacemaker, he alone thought that it really had a future. And he looked at me sort of funny, and he walked up and around the room a couple of times. He said, you know, he said, if you can do that, he said, you can save 10,000 lives a year.
In 1958, a medical team implanted the first heart pacemaker. But there was still one major problem.
After the first 10 years, we were still only getting 1 to 2 years out of pacemakers, 2 years average. And the failure mechanism was always the battery. It didn't just run down, it failed. It was the human body is a very hostile environment. It's worse in space, it's worse in the bottom of the sea. You're trying to run things in a warm, saltwater environment. The first pacemakers could not be hermetically sealed, and the battery just didn't do the job. Well, after 10 years, the battery emerged as the primary mode of failure, and so we started looking around for new power sources. We looked at nuclear sources, we looked at biological sources, letting the body make its own electricity, and we looked at rechargeable batteries, we looked at improved mercury batteries, and we finally wound up with this lithium battery. It really revolutionized the pacemaker business. The doctors have told me that the introduction of the lithium battery to pacemakers was more significant than the invention of the pacemaker in the first place.
Why does lithium make such an improvement in batteries? Lithium is a very light and reactive metal that can be oxidized very readily. Lithium's highly reactive nature is due to its exceptional ability to release electrons. So whereas the standard single-cell battery produces 1.3 volts of electricity, the single-cell lithium battery produces 3.4 volts and has twice the life of the alkaline battery. Out on the open road, we use a wholly different type of battery. These are the batteries which have started our cars and kept them running year after year. They're lead storage batteries, and they differ from the single-cell batteries we've seen so far. For a start, each one has several cells. Inside the battery are different electrodes, lead and lead dioxide. they're immersed in sulfuric acid. In use, a reaction forms lead sulfate on both electrodes. Atoms on the lead electrode are oxidized to a white coating of lead sulfate. Lead dioxide is reduced to lead sulfate. Electrons released from the oxidized lead can do work such as turn a car's starter motor. They travel on to the lead dioxide and reduce it. White lead sulfate gradually coats both electrodes. To recharge the battery, an alternator pushes electrons in the opposite direction. The chemical reaction reverses and the battery is recharged. Batteries use chemical changes to make electrical energy. The reverse process, electrolysis, uses electric current to cause a chemical change, such as separating water into hydrogen and oxygen.
An electric current is passed through two electrodes. At the negative electrode, we see some gas being given off. That's hydrogen gas. The hydrogen ions are gaining electrons and then providing hydrogen gas. So this is a reduction process, the gain of electrons. At the positive electrode, oxygen gas is given off. In the process, electrons are lost. The loss of electrons is oxidation. So what we're seeing now is the decomposition of water.
In industry, electrolysis is used to extract aluminum from aluminum oxide ore. Inside these smelters, aluminum oxide is dissolved and electric current applied. The electric current breaks the bond between aluminum and oxygen, reducing the oxide to aluminum metal. Looking to the future, another application of electron transfer is the solar cell. Absorbed light energy causes a reaction that releases electrons, producing an electric current. Powered by solar cells is the Sun Racer, a winner for General Motors and for electron transfer. It converts sunlight directly to electricity. When it's cloudy or when it needs an uphill boost, silver-zinc batteries help. Future transportation and electron transfer in action. To review, oxidation and reduction reactions involve the transfer of electrons. Electron transfer occurs in corrosion when metals are oxidized and oxygen is reduced. Chemical reactions change chemical energy into electrical current for doing work. The energy from electron transfer can be harnessed in batteries of different types. Electric current can cause chemical change that otherwise wouldn't occur. This is called electrolysis. And electrolysis is used to make aluminum from aluminum oxide. Electron transfer, oxidation and reduction, is at the heart of present and future invention.